Lighthouse Scientific Education presents a lecture in the mole series. The topic, atomic mass and molecular weight. The similar terms formula weight and molar mass are also discussed. Material in this lecture relies on an understanding of the previous lectures, the mole as a quantity, and from the measurement in number series, scientific notation. The lecture begins with definitions and principles for atomic molar mass and molecular weight, formula weight, and molar mass. A set of basic rules are covered for determining these weights or mass. 3 practice problems are given. To definitions. Molar mass is the mass of 1 mole of an element or compound. It is given as mass per mole, and the units are grams per mole. In the previous lecture, it was shown that the mole is just a number, a counting unit. It is a very large number because atomic scale particles are very small. It is called Avogadro's number and is usually written in scientific notation. Often just the first 3 numbers of the coefficient 6.02 are used. Atomic molar mass is the molar mass of an element. It is the weight of a mole of a single type of atom. Molecular weight, abbreviated MR or MW, is the sum of the atomic molar masses of each atom in a molecule or polyatomic ion. It is very similar to molar mass, and the 2 terms are somewhat interchangeable. Molecular weight is the more commonly used term. Formula weight is the sum of the atomic masses for a formula. Molecular weight is a formula weight. Formula weight is a bit broader because it includes ionic compounds. For a molecule, any of the 3 terms, molar mass, molecular mass, or formula mass, can be considered correct. Use the one that your instructor favors. We'll be favoring molecular weight. Let's dig a bit deeper with atomic molar mass. It is the molar mass of an element. It includes the relative abundances of the element's isotopes. That is, for a single element, the different isotopes that its atoms come in. These are in specific proportions. The atomic mass of an element is Avogadro's number of atoms in those regular or specific proportions. To make matters easier, the atomic molar mass is given as the mass number of the element on the periodic table. Calling up a periodic table and taking a closer look at the element carbon shows the atomic number written at the top of the symbol and the mass number at the bottom. The atomic molar mass of carbon is 12.01 grams per mole. A look at nickel. Its mass number is 58.69. The atomic molar mass of nickel is 58.69 grams per mole. Silicon has a mass number of 28.086. The atomic molar mass of silicon is 28.086 grams per mole. Getting atomic molar mass is a straightforward process. Molecular weight of a compound is a bit more involved, but it can be broken down into relatively simple steps. The rules are given for molecular weight, but they also work for formula weight and molar mass. As mentioned, molecular weight is the sum of the atomic masses of each element in the molecule or polyatomic ion. It is found by getting and adding all of the atomic molar masses of all of the atoms in the formula. For example, the molecular weight of H2O is the sum of the atomic mass of 2 hydrogens and 1 oxygen. The molecular weight of ammonia, NH3, is the sum of 1 nitrogen and 3 hydrogen atomic masses. And the molecular weight of the sugar glucose, C6H12O6, is the sum of 6 carbon, 12 hydrogen, and 6 oxygen atomic masses. Determining the molecular weight of a compound is an essential skill moving forward in the study of chemistry. We should therefore consider and practice the process. A basic 4-step process can be constructed that yields a molecular weight. It begins with the chemical formula. What is the compound? What atoms is it composed of? What is the ratio of the atoms in the compound? These are some basic questions asked and answered in this step. From there, get the atomic molar mass for each element in the compound. Using the formula and the atomic molar masses, multiply the subscript for each element in the formula by its atomic mass. If there are 2 hydrogens in the formula, multiply the atomic mass of hydrogen by 2. Finally, add together all the masses calculated in step 3. That value will be the molecular weight. Most students master this process after solving for a couple molecular weights on their own. Let's put these rules to work with the first example. The formula is that for water, H2O. The second step says to get the atomic molar mass for each element. Calling up a periodic table, the atomic molar mass for hydrogen is 1.008 grams per mole. Write that down. The atomic molar mass for oxygen is 16.00 grams per mole. Write that down. Step 3 has us take the atomic molar mass for each element, we'll start with the hydrogen, and multiply it by its subscript in the formula. Hydrogen subscript in the formula is A2. That gets a value of 2.016 grams of hydrogen per mole of water. For oxygen, its atomic mass is multiplied by 1, since its subscript is a 1 in the formula. As we know, when the subscript in the formula is a 1, it is not written, but instead implied. Additionally, there is no need to multiply by 1 because it does not alter the value. There are 16.00 grams of oxygen in a mole of water. These are the values needed for the addition in step 4. Write out the addition and sum. The molecular weight of H2O is 18.016 grams per mole. That is, 1 mole of water has a mass of 18.016 grams. One final note needs to be made. Since addition was done with values that have different significant figures, a check is needed to make sure the final answer to the process has itself the correct number of significant figures. Not all instructors are sticklers for this point, but we will treat them like they are. First to the hydrogen. Its last significant figure is in the thousands place. After the decimal point, it goes tenths, hundreds, thousands. The oxygen, the final sig fig, in its atomic mass is in the hundreds. The rule for adding or subtracting numbers has the answer of the math having significant figures that match the starting value with the least amount of information in its value. That would be the oxygen, since it does not have information in the thousands. This means that the molecular weight of water can only be given to the hundreds position, like the atomic molar mass of oxygen. The 6 in the thousandth position will still play a role in the rounding of the 1 in the hundreds. Since 6 is larger or equal to 5, the 1 is rounded up to a 2. The molecular weight of H2O, as calculated here, is 18.02 grams of water per mole of water. For those who need it, there's an entire lecture on significant figures in the measurement and number series. Example 2. And the formula is that of the ion carbonate, CO3 with a -2 charge. This example will show that molecular weight of an ion are determined the same way as any other compound. That carbonate has an extra 2 electrons, but they do not affect the molecular weight, since electrons have a tiny fraction of the mass of the other subatomic particles, and are therefore treated as insignificant contributors to the overall mass. Step 2, get the atomic molar mass for each element. Calling up the periodic table, starting with carbon and its atomic mass of 12.01 grams per mole. Keep track of that. Then to oxygen. Its atomic molar mass is 16.00 grams per mole. Keep track of that. Step 3 has us take the atomic molar masses and multiply them by the element subscripts. For carbon, that is 12.01 grams per mole times the subscript of the implied 1. That math is easy. There are 12.01 grams of carbon in 1 mole of carbonate ion. For oxygen, its atomic mass is multiplied by the 3 in the chemical formula. That gives oxygen's contribution as 48.00 grams. What about the charge? Nowhere does the -2 charge come into play in getting molecular weight. These are the values that are added together to get the molecular weight. 12.01 plus 48.00 gives a value of 60.01 grams. 60.01 grams of carbonate is the weight of 1 mole of carbonate. A quick check of sig figs shows both the atomic molar mass of carbon and oxygen to go to the hundredths place, as does the calculated molecular weight. It has the correct number of significant figures. Example 3 is a larger molecule. It is a sugar molecule with a general formula of C6H12O6. In step 2, we get the atomic molar mass for each element. Using the periodic table, carbon, as we might remember, has an atomic molar mass of 12.01 grams per mole. Hydrogen has an atomic molar mass of 1.008 grams per mole, and the atomic molar mass of oxygen is 16.08 grams per mole. For step 3, these values are multiplied by their respective subscripts. Carbon's atomic molar mass is multiplied by the subscript 6 for a mass contribution of 72.06 grams. Hydrogen's atomic molar mass is multiplied by its subscript of 12. That math yields a mass contribution of 12.096 grams. And finally, the 16.00 grams of oxygen is multiplied by 6. 16.00 grams times 6 is 96.00 grams. There is 96.00 grams of oxygen in 1 mole of the sugar molecule. Take these 3 values and add them up. 72.06 plus 12.096 plus 96.00 equals 180.156. There are 180.156 grams of sugar in a mole of sugar. And significant figures? Both the carbon and the oxygen have atomic molar masses given to the hundredths. The final answer must therefore be rounded to the hundredths. Does the 5 in the hundredths stay a 5, or should it be rounded to a 6? That 6 that follows the 5 says round up for a final molecular weight of 180.16 grams per mole. Another way to handle the sig fig issue is to find the atomic weight of oxygen and carbon that goes to the thousandths position, like the hydrogen. To recap the lecture, molar mass is the mass of 1 mole of an element or compound. The units are grams per mole. A mole is a number, 6.022 times 10 to the 23rd. Atomic molar mass is the molar mass of an element. It is the mass of 1 mole of an element. The mass includes relative abundances of the element's isotopes. Importantly, it is given as the mass number of the element on the periodic table. The molecular weight, as well as the formula weight and the molar mass, of a compound or polyatomic ion is found by having a formula, getting the molar mass for each element in the formula, multiplying each element's subscript in the formula by its atomic mass, and finally adding all the masses calculated in the previous step. And that concludes the lecture. Practice getting molecular weights. They are an important tool. And then go to molecular weight and conversion lecture to further develop the concept.